Hi friends, in today's video we are going to discuss about the vector calculus part. And in my last few videos we have discussed about the coordinate system, in which we have discussed three kinds of coordinate system: Cartesian coordinate system, cylindrical coordinate system, and spherical coordinate system. And we also have discussed several parameters in case of each of the coordinate system. So if you haven't watched those videos, so I will refer, please watch those videos first. After that, you can study that vector calculus part. Now, the vector calculus is very much important, and it is also a introduction to these, also introductory part in case of the electromagnetic theory, because the vector calculus part will be used everywhere, almost in and every chapter of this electromagnetic theory. So let us discuss this vector calculus part very crucially and very effectively. So each and every point I am going to discuss over here. So let us start this vector calculus. But before diving into the vector calculus, I want to introduce you a operator that is called the del operator. So first point is very much important. I am going to introduce a operator that is called a del operator over here. And what is the del operator? Now the del operator is nothing but the differential operator. Okay, it is called the differential operator. And how the del operator actually is, or what is the equation of the del operator? That is, this del operator can also be written as, just a minute. Okay, yeah, that is 1 by h1 dou by dou u into au plus 1 by h2 dou by dou v into av plus 1 by h3 into dou by dou w. That is nothing but the partial derivative, dou by dou w into aw. As you can see, this operator has the three directions, that is au, av and aw. That is nothing but the three unit vector. That means it is a three-dimensional vector. Okay, so the most important thing, that is the del operator is nothing but a vector. Okay, this operator, this differential operator is nothing but a vector quantity. You have to remember this. Okay, very crucial. So this del operator is vector quantity. Okay, now depending upon several operations on this del operator, I have deduced so many parameters in case of the vector calculus. So let us see what are those parameters actually. Now the first thing that I want to discuss, that is the gradient. Gradient of a scalar. Gradient of a scalar. That can also be written as del V. Just one thing I want to mention over here. This is not the normal delta. It is the inverted delta. Now, gradient of a scalar, that is the del V, that I am going to discuss first over here. Okay. Now the things are, this delta, this is nothing but the differential operator. This V is nothing but the scalar. This V is nothing but the scalar quantity. Okay. So that's why I have written over here, that is the gradient of a scalar. This del into V, that is the dot product of a scalar quantity with this differential operator, that is nothing but the gradient of a scalar. Now you might ask me a question, why the gradient of a scalar is so important, where it is actually used. See, first of all I will discuss its use case with an example. Then it will be very much easier to you for understanding the del V operator. Okay, so actually the gradient of a scalar, okay, first of all let me discuss like that. I am drawing a three-dimensional plane over here. That is x, y, and z. Say there is a three-dimensional plane, and inside this there is a surface or the plane. Say, okay, this is a three-dimensional plane. Sorry, this is a plane or the surface. This is also called a surface in the three-dimensional vector space. Okay. Yeah. Now this is what? Plane. This is actually the plane, or you can also call it as a surface. in 3D. In 3D, there is a surface like this. Okay. Mhm. And now I want to determine, say, now I want to determine, mm, now I want to determine a normal vector on this plane. I want to determine what? A normal vector on this plane. That is, just a minute. Say this. I want to determine this. This is nothing but a normal vector on this plane. Okay. And this is nothing but the unit normal vector on this plane in the three-dimensional vector space. That is the xyz. In the xyz plane, there is a surface or plane, and upon which I am trying to determine this unit normal vector. And if I try to determine the unit normal vector in upon any plane, then we need the help of the gradient, because you can see any plane, this plane, for example, this plane, any plane is a scalar quantity. See, say the plane is, say there is a plane equation has been given, and this plane has been determined, has been denoted by the v, because any plane is a scalar quantity. And say the equation is x plus by plus cz plus d equal to 0. Why? Because this any plane is the function of x, y and z, that is ax plus by plus cz equal cz plus d equal to 0, right? Now if this occurs, so this is nothing but the v, because any plane is a scalar quantity, and that is also the function of x, y and z. Okay, that is the same plane, that is this plane I am talking about. Okay, this plane v, scalar quantity, right? So now if I want to determine the unit normal vector, that is the an, if I want to determine the an, then that an can be given as del v whole divided by modulus of del v. Okay. That is the unit normal vector. Okay. That is the unit normal vector. This unit normal vector can be given as del v by modulus of del v. That is the actual formula. So why the gradient is here? So that I can write like this. It is used to determine, or it is used to find the unit normal vector to a line or surface or any scalar function. Basically, any scalar function means with any v. Now the v can be line, surface, anything, because but the v should be the scalar function. Okay, that is v can be, v should be a scalar function that can be the line, surface, etc. Line, surface, etc. Those are nothing but the scalar function. So v can be any scalar function, and if I want to determine the unit normal vector upon any scalar function v, that may be line, surface, etc., then I need to determine the gradient of a scalar, because the formula of an, that is the unit normal vector, that has been given here by del v upon modulus of the del v. Now, as you know, del v is a vector quantity y. So let me reduce the equation of the del v. Then you will understand why the del v is a vector quantity. See, del v. Now you know the delta equation or the differential operator, right? So just write like this. 1 by h1 dou by dou u. Now v is a scalar function, so into v I can write into au plus 1 by h2 dou by dou v, and v is a scalar function, that is the v in the direction of ab. As the v is a scalar function, that's why v will be multiplied with each and every component of this del operator. That is nothing but the v will be multiplied with v will be multiplied with dou by dou u. It will be multiplied with dou by dou v, and it will also multiply with, that is, dou by dou w. So that is nothing but I can write, that is 1 by h3 dou by dou w into v. Just a minute. There is a space shortage here. Okay, just a minute. Small space shortage occurred here actually. That will be del v will be what? It is nothing but the 1 by h1. I can directly write it like dou by dou u into v. That is the dou v by dou u in the direction of au plus 1 by h2 dou v by dou v in the direction of ab plus 1 by h3 dou v by dou w in the direction of aw. Right? Because the v is a scalar, and that v will be multiplied with each and every component of this del operator. Okay, it will be multiplied with each and every component of this del operator, like this. Now what is the u, v and w? U, v and w, those are nothing but the parameters. And h1, h2 and h3, what are those three? Those are nothing but the scaling factor. In my last video I have discussed about it, because in my last video I discussed the analytical approach of the differential length, area and the volume. In there I have discussed about it. If you haven't watched my last video, please watch those videos first. This is nothing but the scaling factor. That is the same scaling factor that I discussed in my last video. Okay. So this is the actual equation. This is the actual equation of our gradient of a scalar, right? So that is the important point. And the important thing that I want to mention over here, why the gradient of a scalar used, that is, it is used to determine, let me write this point also here, okay, just a minute. Hmm. It is used, why it is used, just a minute, let me write in different font. It is used to find out or determine the unit normal vector to any scalar function. Now, the scalar function may be what? Line, surface, etc. Okay, line, surface, etc. Okay, this is the thing. That is the use to determine the any unit normal vector. Now the unit normal vector means that is actually your an. Unit normal vector means what? Nothing but your an. That is the unit normal vector. Okay, that is the unit normal vector. Right. And this is the very much important thing. Okay. So that's all about our gradient of scalar. Okay. So that's all about it. In my next class, I will discuss about the concept of flux. Okay. So that's all for now. Hope we will meet you soon. I think you have understood this gradient concept very easily, and I have tried to make it more and more easier. Okay. So hope we will meet you soon. Thanks for watching.